scientifically, that's what makes sense. There is corresponding to this a time scale as well, and I'll get to that in a little while. Here's a different set of data sets or data that we have. And these are where we have a particular, and there's the damage number, 1250. And what I'm looking here is at different neutral density filters. Different neutral density filters. And the chemical reaction here is linear for a while, and then they tend to level off at a certain level. So that's the sort of path that we see in this degradation. Okay, so this is different neutral density filters, and probably at one particular wavelength. I don't remember which wavelength that is. Okay, so dosage, as I mentioned a moment ago, is the scientifically relevant time scale. Okay, so it's proportional to the number of photons that are absorbed into the material. See, sometimes a photon hits the material but doesn't get absorbed. Then it doesn't do any damage. It just sort of bounces off. This dosage is computed using this double integral here, where, so it's sort of cumulative dosage, it's the number of photons absorbed, so we're integrating over time, because this is a process that goes on over time, we're building up cumulative damage, and then this is integrating over the different wavelengths, because remember that the small wavelengths are causing more damage, the larger wavelengths are causing less damage. This is what is known as the spectral irradiance, and it is a function of the wavelength and time. And so you can think of that as being the whole spectrum. And then this factor here sort of looks like a probability distribution. Well, in a sense, that's what it is. It gives the proportion of photons that will be absorbed into the material, and that depends on the wavelength. Again, the higher energy ones have a lot of energy. They're more likely to get inside of the material. Okay, so this is dosage up to time t. Sort of a pure dosage, but here we're interested in the effective dosage. And the effective dosage has this additional factor in here, which is known as the quantum yield. So quantum yield is a concept of photodegradation. And it also depends on wavelength. And it's a function that allows that at small wavelengths there's more damage. Not just because of the absorbance here. I mean, that's true too, as I said on the previous slide. But given the same proportion getting in, when it actually gets inside, if it's high energy, it will cause more damage, given that it got absorbed in. So we need this extra term here to account for that. And in the photodegradation literature, they call that quantum yield. And we call it quasi-quantum yield because we're sort of measuring that thing empirically, based upon our data. We're estimating that function here. Okay, now we've got a lot of data where we were varying all of those factors. UV spectrum, UV intensity, temperature, and humidity. And as we generally should do when we're trying to build up a model, we don't want to make any assumptions at the beginning. So what we do then is we fit a categorical model, where we just say we've got these different combinations of those four factors, and we want to empirically see what effect they have without making any assumption about the functional form. Okay, ultimately there will be a functional form, but we don't want to assume anything about the function of temperature, the function of relative humidity, function of the neutral density filter, and so forth. We don't want to make assumptions about those things. But we want to fit a model, so we fit this categorical model. So it's sort of like running an experiment where you might have something as an effective temperature, okay? A lifetime and how it's affected by temperature. And you might want to fit a regression model to that, where high temperature lifetime is shorter. But I don't want to make that assumption about the functional form. So I just fit separate models at each temperature. And then empirically look to see how does the lifetime change without making any assumption. So that's really what we're doing here. That's what we mean by categorical model.
You treat temperature and humidity as different entities.
Yes. Yes.
You have the model simple or?
That's right. We treat them, we're testing at different combinations of those, but we're not going to assume what the functional form is yet.
Humidity and temperature, they're not related. We assume that.
We can control those in the experiment. Now, in real life, they might be related, but the model should still be valid if we hold those constant and estimate the relationship between degradation and the experimental variables. So that's what we're doing now. We're using these experimental data taken from the lab to find out what's the functional form of the relationship. But we're starting off with a categorical model so we don't make any assumptions about these functions here. This is the curve we're ultimately going to fit. And this was, the form of this is just curve fitting. So we said, oh, here's a nice curve that can be used to describe. The alpha here is the asymptote. And then the values of mu and sigma control the shapes of these curves, how fast it goes down, and the location of the curve in the usual kind of way. And so this is the amount of damage as a function of time. Okay, now that's the underlying model that we think about here, the shape of these curves. The actual model for the data is very similar. The difference here is I've got an error term, just like in usual statistical modeling. When I fit a model, the points aren't going to be right on the curve, so we have the error term that allows the points to deviate from the assumed model. And we also have this term here. This is new as well. So we added this term here. That's a random effect. That's a random effect, and so the nu sub I for each unit is a random variable that allows for unit-to-unit variability. We can see this variability in the data. So for example, you can see that these are all the same test conditions, but there's variability here. That random effect is allowing for unit-to-unit deviations from some sort of center version there. Okay? And again, at the end of the day, this is what we're going to be doing. We're going to model this Z as a function of the experimental variables, bandpass, temperature, relative humidity, but we don't want to make assumptions about the function here, the function here, the function here, and so forth. So we start off with this categorical model. And all of the model fitting is done in R, using the nonlinear mixed effects model function. Very powerful function to do this nonlinear curve fitting where you've got random effects. And here's kind of the results that we got from our categorical model. So here's the temperature effect. It's nice and linear. So that's a nice simple one. We've got a bandpass filter effect here, which is not far from linear. And in effect, what we're doing there is looking at the effect of wavelength. Looking at the effective wavelength. There it is right there. There's the wavelength. There's the temperature wavelength. And this is the effect of the neutral density filter. And the effect of the neutral density filter is really modeling the fact that the numbers, when we buy those filters, are not exactly true. If it says 10%, it might be 8% being passed through. So we're trying to build a model to explain that deviation. And then this was the surprise here. The relative humidity tended to be high at low humidity. We call this the dry condition. And also tend to be high at the higher humidities and low in between. This is a surprise to the scientists. And once they discovered this, they began to study, well, why is this? They have some explanations, but they didn't polish those explanations in time for us. So here, we're going to describe this by kind of an empirical quadratic model. Again, just curve fitting, so we can put all of this together. So after looking at these results from the categorical model, then we're ready to assume some functional form. And here's sort of a description of the functional form. For temperature, as is common, we use something called Arrhenius. Arrhenius was a Swedish, Svante Arrhenius was a Swedish chemist who in the late 1800s did a lot of scientific work to study rate reaction and how it is affected by temperature. Rate reaction and how it is affected by temperature. And he came up with this relationship here, which basically says that the log of the rate is linear in reciprocal Kelvin. The log of a chemical reaction is proportional to reciprocal Kelvin. So it's very commonly used in accelerated testing where there's temperature acceleration. The relative humidity effect, as I said, we don't have any science for that, so we just fit this quadratic model here. And here's the coefficient that we will estimate. Here's the coefficient we estimate here. And then the effect of the bandpass effect, again, this is the quasi-quantum yield, the effect that wavelength has on degradation. So again, we sort of, actually this relationship here, we saw in the categorical model, sort of this one here, but we also see that in the literature as well. So other people have discovered that relationship, so it's nice that sort of agreed with what we were doing. And the neutral density relationship, we use as power function. Now, there was one surprise here, and that's this point here. I didn't comment on that, but that point didn't follow the data very well. And that turned out to be a point, it was an experimental point all by itself, at high temperature and high humidity. And there was no explanation for why that happened. It was thought that maybe there's an interaction effect. So that's what we did when we did the regression modeling. We put an interaction term in to, I would say, accommodate that outline. To accommodate that outline. Okay. And then we also have a functional form for the sigma parameter. So again, this is what we discovered when we did these separate categorical models, that the sigma parameter sort of has this shape here, and we use this functional relationship here to sort of fit a curve through that. Now we can bring all this stuff together. Now that we've identified the shapes of these functions, we can bring them together, and this is the final model that we get. And now when we run that through NLME again, there's fewer parameters. Because when you fit the categorical model, there's lots of parameters there. Because you got all these dummy variables to allow for the different categories. When we start fitting functional forms, the number of parameters goes down. There's still a lot of parameters there, but the number of parameters is considerably smaller. So these are the parameters of the final model that we ended up using. This is just a table of the parameter estimates. One thing you can see is that the parameter estimates are all very highly significant. The p-values are extremely small. We were having a little debate about p-values yesterday, and I said, I like p-values for certain purposes. This is one where I like them. So you can look at that and say, everything's highly statistically significant. It's easier than looking at the confidence intervals. We feel good about this. What I'm plotting here are paths from the data and the fitted model. Okay, so when we do regression analysis, we often take our fitted line and see how does it agree with the points. The agreement here is really excellent. So there were many of these paths, and we just picked sort of randomly 3 or 4 of them here to show you. And this is typical of the kind of agreement that we were getting. No surprise here. We have data. We very carefully built up the model using a combination of what we expect to fit and the categorical model that led us toward this functional form. So it's really no surprise that we get really good fits here, because we put in all the model terms that would almost assure that we would get this kind of fit. Of course, in practice, we have to worry, how well will this model actually work if we were to do the experiment again? Or in this case, how well will the model work to predict the outdoors? So that's where we're going next. This is the outdoor experiment, which I've already mentioned and talked a little bit about. The basic objective is to see if the indoor test can predict the outdoor results. So these were conducted on the roof of a building at NIST, and the scientists there were very busy because they were periodically taking the lab specimens and having to do the FTIR, that's labor intensive, and then every 3 or 4 days they would bring down the specimens from the roof and do the chemical analysis as well. So they were very busy for many months gathering all this data. It was actually years, like I said, 2002, 2006. 4 years they were doing this data gathering. So it was a huge amount of work. So as I said before, same variables, except they're not being controlled, of course. They're outside, but they were being measured. And we were getting data at 12-minute intervals. So that was my first exposure to big data. That's a buzzword now, but in engineering, a lot of the applications I deal with small data. This was my first exposure to big data, and that's why I said to the leader of the group, I said, you've got to help me with a graduate student. I'm too old for big data. We need one of these young people that can deal with the big data. So I had a graduate student who did some of this work with me. And, so every 3 or 4 days they would bring these panels down and test the individual units. Now, here's a sampling of some of the outdoor exposure data. Now, the first thing that you see when you look at this plot is, wow, there's a lot of variability there. You look at these, they're coming down very fast, and you look at these, they're coming down slowly. It turns out there's a very good explanation for what's going on there. It's not as bad as it seems. So what's happening is these are units, okay, so in Maryland, probably a bit more than you have here, we have different seasons of the year. And in Maryland, it can be cool in the winter, meaning they actually sometimes get snow, so it gets below 0 C from time to time. And in the summer, it can be very hot, where you can get up to 33, 34, 35 C for periods of time. So you have these temperature ranges. You have more light in the summer and less light in the winter. So there's quite a bit of variability. And so these units were probably put out into exposure maybe in May, where there's a lot of light already. And so May, June, July, and after 2 months, they're already failing here. So maybe it was June and July, where you have the most sun. This unit, on the other hand, probably went out into exposure maybe in October. So it's going down a little bit fast, but then you get into November and January and February, where there's not much light. There's a lot of clouds and there's just not much sun, and so it levels off there. It's not degrading very rapidly. But then you get out into the springtime, and again, you're into May and June, and then it starts going down rapidly again. So the huge difference between these units is driven by when they went into service. I might add that the particular coating that they were using here was an unprotected epoxy. And they used it, when I say unprotected, when I go outside for any period of time, the instructions from my doctor is I have to put this sunscreen on my hands so that I don't get damage. And when you have a paint and a coating, you can mix something like, it's the same chemical, you can mix that in to the coating and it will protect it from the sunlight. It will last long. It's very expensive to use it, but these specimens did not have that because we wanted to get results quickly. Otherwise, they might have had to wait, instead of months, they might have to wait years to see an important amount of damage. So that's kind of another accelerating factor that was being used here. And here's, this horizontal line is the damage level. We say when it gets down to there, that it was bright and shiny at the beginning. By the time you get down to there, you can't see the shiny anymore. And that's how we chose this level. I'm going to choose just one of these curves. And here's the observed weather, as I call it. So weather is, well, here's the amount of damage. So I'm choosing this one here. There's the damage. And here's the temperature. So just as I said, it's sort of warm, and then it gets cool in the winter. That's this period here. And then we're getting into the spring and summer again, and the temperatures are going up. This is the UV spectrum, and this is UV time. And again, you can see in the summer, there's more UV than in the winter. The levels are down here. This is over time. The levels of UV are down in the middle here, but they're up here and they're up here. And this is relative humidity in Maryland. It's always humid in Maryland, and that's why there's no seasonality, basically. There is no seasonality. There is seasonality in UV, there's seasonality in temperature, but not in humidity. Okay, so the model for the outdoor prediction, basically we can take the model on the indoors, and we use the indoor model conditional on the observed weather. Conditional on the observed weather, as I call it. And then we can see what is the agreement. So this is just a sort of discretized version of predicting what will happen outside as a function of the weather. I'm running out of time now, so I'm not going to go through the details of the formula, but basically it's the same formula we fit inside, except we've discretized over 1 hour. So 1 hour, and we also discretized the spectrum by 2 nanometers, and that just allows us to do this integration. And then for each of those discrete parts, the 2 nanometers each hour, we get a predicted amount of damage. And then we just integrate those up over time. And we get then how much damage for that interval, and then we sum those up. And that gives us the prediction for the damage. Again, the model comes from the laboratory data. The covariates that drive the model come from the observed weather. And then this is the sort of agreement that we get. So you can see the data points, the actual amount of damage, and then the black line is the prediction. Predictions are never exact, so we see some variability in the prediction. They don't all agree, and that's taken care of by the random effect. We're predicting, when we predict that that random effect is just 1, but we know it's not 1, but we have no way of predicting that random effect. So sometimes the fitted curve is above, and sometimes it's below because we don't have perfect knowledge on that random effect. We just assume it's 1 at this point. Remember, it's a multiplicative factor. But sometimes it agrees almost exactly. And then the blue lines here are kind of prediction intervals. We'd be very surprised, given our model, if we had an observed that went outside the prediction limits here. So this is doing pretty good, I would say. So again, this is the prediction from the model, prediction intervals, and the observed data are always inside the prediction intervals. Now the next thing we did, let's see, this is this is just sort of averaging all of these. It says on the average we're pretty good. And then this is similar to this curve here, except now what we're saying is let's take a little bit of early observation for each unit. A little bit of early observation for each unit and predict that random effect. So this might be, in real life, might be something like, what is the environment? Or whatever it is that's causing that random effect. And if we do that, then we get much tighter bounds, we get much better agreement. So this says that this is important from a point of view of this modern topic that we hear a lot about called prognostics, which says, I've got a unit that's been out there in the field. I want to know what's the distribution of remaining life. So you can look at the early history of that unit and then predict the rest. And that's sort of what we're looking at here. How well can we predict an individual unit, given that we have some history on that unit, plus all of the other information that we've got from the other units, which in this case was all of the other information that we have from the laboratory. So now I'm saying we're observing this unit in the field for a little while. I'm going to use that information to estimate the random effect, and then use the rest of the information to predict the remaining life of these units. Okay, so here's my concluding slide. What we did in this project was to take the data that the scientists at NIST collected, and we built up a model for the data based upon physical motivation and some of the ideas we learned about in the photo degradation literature, and put together this model that will predict lifetime as a function of these 4 factors: UV spectrum, UV intensity, temperature, and humidity. Then we built a time series model for the weather. It was basically a multivariate time series for those 4 factors: UV spectrum, UV intensity, temperature, and humidity. And then we used that time series model to make predictions about what those units would do in the future. Actually, this says could be used. We didn't do that. We made our predictions conditional on what had been observed. But in practice, we don't know the future weather. But we can predict it. And so there's going to be some uncertainty there. And we can quantify that uncertainty from the prediction. We can predict the weather and then run that through the model, and we can get some uncertainty because of the uncertainty in the weather. we did had to do with Maryland in the United States, because that's where the experiment was done, that's where we could predict the weather. But you could apply the same model, because the model was done in the laboratory. That laboratory could have been any place. And we believe that this model is transferable once you know the weather in Cochin or any place else where you wanted to apply the methodology. At least for that particular chemical compound, that particular epoxy that we studied. And also the methodology can be applied to paints and coatings that are different than the epoxy, but you'd have to run another set of experiments for that paint and coating, which might have UV, what they call UV inhibitors. The UV inhibitor is what I mentioned before, that goes in the sunscreen that protects compounds from the UV to some extent. And the ideas that we have here, we think could be applied to other places where UV is important. So LED arrays that are being used more and more for outdoor lighting. Certainly for solar cells that are becoming more and more popular because it's clean energy. But those things have a limited life, and one of the main mechanisms is photodegradation. So I know the scientists in NIST are working on these kinds of projects today, going beyond what we did in the original project. Corrosion in a pipeline, and also other kinds of things that, so this is UV, but the general methodology could be applied to other kinds of degradations that happen. So in Iowa, we have a very big wind energy business, meaning that the energy companies are building lots of wind towers, and there's a lot of manufacturing of these things in Iowa as well. And there's a lot of concern about reliability of these things. So I've had we actually have a PhD program in wind energy at Iowa State. And I've been somewhat associated with that. And reliability is a big issue for this. And so we think some of these ideas can be applied there as well. Well, thank you for your attention. I'm sorry I went over a little bit, and I'd be happy to answer any questions that you have.
Any questions?
What you have used is a power conservation
Right, so the question is, you've used things like power functions for humidity and some of the other factors. So in the case of the uraniums, it's just traditional. In the case of humidity, we saw this kind of behavior that was purely empirical. We said, oh, I think we can fit that with a quadratic curve. And the other one, we saw the damage going down exponentially like this for the quasi quantum yield and sort of approaching zero, the amount of damage approaching zero as the wavelength gets bigger. We said, oh, that was a nice exponential function. So that's what we fit, but we also saw that used in the literature as well. So the categorical model is how we got there, because then we can see the shape of the function without making any assumptions about the function. And then we just find something that either is physically justified or that just fits the curve well. And the range of the variables was such that we're not doing much extrapolation in these problems because we experimented over this pretty wide range.
Any more questions? If no more questions, let's thank the speaker. So on behalf of Cochin University and especially the Department of Statistics, I would like to thank Professor Meeker for getting all the way and coming here.
thank you all for coming.